Every company in metal extraction has been using this for a long time, probably 20 or 30 years. Why aren't you using it?
There's a reason they came up with the saying about hammering nails with a microscope.
We stepped on the same rake again, but actually, absolutely no conclusions were completely drawn from it.
So, at best, you just have a batch sitting idle, and at worst, that batch has already caused problems that should have been avoided. And that is quite literally just burning your money completely for nothing.
There are already implemented projects where we take material directly from the conveyor belt, crush it, and feed it onto a parallel bypass conveyor where you can easily install an XRF device that will accurately determine the silicon, calcium, and iron content for you.
Gold mining companies are actually some of our favorite clients because they don't really count their money and they buy a lot of equipment.
And almost all gold mining enterprises, of which there are a huge number, are simply not equipped with any inline analyzers at all.
That's where the questions start to arise.
Dear viewers, good afternoon. My name is Arseny Trushin. I am the director and owner of the company which specializes in the production and development of X-ray fluorescence online analyzers for process streams. Today we have Alexander as our guest, a colleague from the SNK company. Alexander, please introduce yourself.
Dear viewers, hello. I am Alexander Kirilenko, Director of Science and Development, not an owner, of the company PVP SNK. We develop, assemble, and supply equipment for analysis. These are X-ray fluorescence analyzers and optical emission analyzers. And while we don't develop or assemble them, we also supply a fairly wide range of other equipment. These include laser spark analyzers and inductively coupled plasma spectrometers. And here I'd like to boast just a little bit. We don't just deliver and forget about the equipment, but we also strive to ensure that our clients don't just buy a fancy toy that gathers dust, but instead, it is fully integrated into the customer's technological process and effectively solves their specific tasks. And actually, it's not as simple as it might seem at first glance, which is why we're having this conversation.
Yes, Alexander, I always feel it's very important for us to talk about the background. So could you please tell us a bit more in detail about your experience?
Yes. Well, as for my education, I'm actually a bit far from chemistry because I'm a geophysicist. And honestly, my professors will probably laugh if they're watching us now. I'm a seismologist specializing in the mathematical processing of seismic exploration data. It's one of the most challenging majors, so we study both math and physics, math with the mathematicians, physics with the physics department. I studied geology with the expert geologists and chemistry with the natural sciences faculty. So after acquiring a broad and diverse wealth of knowledge in a wide range of academic fields at the university, I managed to somehow synthesize these various disciplines and evolve into the person I am today. Nevertheless, I also have extensive experience working in geophysical fieldwork.
How many years?
I went there each and every single year for 4 consecutive years. In total, I spent about a year and a half in a variety of extremely remote and isolated locations. More than once I had to retake exams in the fall, or closer to winter because of this. But everyone there understood and forgave me, because that's just the inherent atmosphere of the university. Fieldwork is an incredible experience, but it's very demanding on your body. My first job was as a geology department specialist, although in reality, I was more of a sales manager. But nevertheless, it was great because the equipment was highly scientific, and in order to speak the same language as the client, I had to study a lot of literature and many methods. I'm actually grateful for that experience. But gradually I started moving as far away from geology as possible. While I was working as a specialist at my first company, I was noticed by a second company that deals exclusively with XRF. Well, actually, not exactly. The company works with XRF, and the department that noticed me deals only with XRF. That's how I ended up in spectrometry. And little by little, from training at Torres Z in spectrometry, so I expanded my qualifications to include optical emission and laser as well. And I ended up where I am now. That is, it's not just about understanding what's needed and installing it, but truly understanding what's needed. Assembling an instrument for that specific task, setting it up, installing it, making sure it works, training the staff, reassembling the instrument, and so on.
Alexander, in terms of your overall experience, how many years is it in total?
I believe that it is certainly at least no less than 12.
12, excellent, yes. I think it's very important to clarify the specific topic at hand. Could you tell me what your professional background is? In today's conversation, we'll be relying heavily on that information. I also have extensive experience in this field. In fact, I successfully defended my dissertation on this exact topic of an X-ray fluorescence analyzer candidate of physical and mathematical sciences in 2012. And since 2012, our company has existed. Well, colleagues, I suggest we move on to the main topic. Today, given Alexander's extensive education and deep professional expertise, we decided to thoroughly cover the important topic of choosing XRF and LIBS equipment. We will discuss optical emission spectrometers in terms of their practical use in the field for geologists, their specialized applications within laboratories, and their role for continuous online analysis in various industrial settings. To put it another way, we'll try to thoroughly investigate this entire subject in depth. Which of these methods is the most highly recommended for specific applications and tasks?
I'll start by saying that there is no such thing as a good or bad method. There is only a method that is either suitable or unsuitable. That's what I want to start with, and it's something we'll keep coming back to. Because as an equipment supplier, it pains me to see an expensive and beautifully assembled device just sitting there collecting dust. Because you need to focus on the specific task you want to solve. And you shouldn't just look at the dry facts, or just at the list of elements you're identifying, or the analysis speed you need. You need to solve a specific task, and for each task, based on its requirements, you choose a method. There is always a method, one that will either get the job done, or do it not as well, or do it perfectly, but at a price that's dozens of times higher than you'd like, making its economic benefit negligible. What I would really like to do in our conversation today is to help our viewers understand at least what essential factors and key criteria they should rely on when choosing what specific products they will eventually purchase, install, or count on for their long-term needs. Because there are situations where one method is better than another, and we will look at those and explain why that is the case. But in exactly the same way, this wonderful method that we were just praising in just a few seconds will be criticizing it, because we will be relying on the specific task and the conditions in which we are working. For example, well, Arseny, you are in favor of XRF. You defended your PhD on it. And actually, I did too. Well, XRF allowed me to buy an apartment, so I'm very grateful to it. But there are a huge number of situations where, honestly, it would be better if it didn't exist at all and wasn't getting in your way, because what you really need is optics and emission. And the opposite is also true. Optics. The emission allowed me to buy a car, so I'm grateful for that too, and I'll be praising it as well. Because of my education and extensive experience specifically in fieldwork, geological and geophysical, I want to explain why XRF as a method is so popular and beloved, particularly among geologists. And the reason is actually very simple. This method is quite easy for the operator to use. Of course, its internal workings are complex. There's complicated math involved, and the instruments need to be calibrated. Well, I'm talking here about factories, and as for the developers, of course they struggle, but the operator doesn't struggle at all. The operator. Because their task is literally to bring it up, press a button, and get the result. And on top of that, modern devices even allow you to link the result to coordinates. So it's almost like semi-magic at this point. What used to take geologists weeks, months, or even years, now a single team can accomplish in literally 2 weeks, provided there's good transportation. This method allows the instruments to be very portable. So you don't need to haul extra equipment on sleds or trucks, or God forbid by helicopter. After all of that is insanely expensive and complicated. But literally, the device is, we jokingly call it a pistol among ourselves. You pick it up, you get the result. So you grab the pistol and get the information right at the work site. And you've already processed it, you understand what's coming next, what we should do next. It honestly sounds like science fiction. I mean, it's something you can take anywhere, and it also provides location-based analysis. And the analysis it gives is quite accurate. Well, it's like science fiction. Why would you need any other analytical methods? But right away, a problem arises. It's not the devices themselves. It's the physics that's the problem. Well, the physics is good, but physics is heartless. This method will probably never, at least not in the foreseeable future, I certainly won't live to see it, allow us to analyze elements lighter than magnesium, and accordingly heavier than uranium. But we don't need to analyze those. They're extremely rare in nature. But for many rocks, for example, the sodium content is important. For a lot of tasks, especially in metallurgy, carbon is extremely important. Right now, lithium is a very hot topic. And XRF just won't help here at all. I'm talking about relatively expensive portable universal devices. And so, Basically, we've immediately run up against the ruthless laws of physics. It's a great method in many ways, but it just doesn't fit for this purpose. Let's take another method, also portable, and which, it would seem, is free from these drawbacks: portable laser spark analyzers. If you look at the description, just the plain specs, the weight is also just about 2 kilograms, it's also portable, autonomous, and you can also link it to coordinates. But if we take the same sample and shoot it with XRF, yes, we see fewer elements, but we see them consistently, accurately, and reliably. The same sample, we analyze it with LIBS. We see a lot more elements, but what we see... Well, to be honest, there are cases where it would be easier to use a random number generator, and even then it would make fewer mistakes. So, it's like the joke that even a stopped clock is right twice a day. For example, in geology, laser spark analyzers are a nightmare. Because with XRF, the analysis spot is large, so we get information that's basically averaged over the entire area, well, over most of the surface area of our sample. Right now, geologists watching us are probably already cursing me. You literally just grab a rock, zap it, and you already get some results. But now, geologists, calm down, because we're going to replace the word rock with rock formation. And a rock formation is made up of minerals. We have minerals in each grain. Just think of granite. It's all speckled, made up of little grains. And with XRF, it immediately scans a certain area, and a large collection of grains eventually settle in that area. And with the spark spectrometer, are we going to discuss how these methods work? But what I really wanted to say now is that with a portable spark spectrometer, we only analyze and measure a very tiny piece of a single grain that makes up our rock. And then, if our hand happens to shake slightly and the device shifts by a couple of millimeters, we're already shooting at an entirely different mineral grain altogether. Grain at a different mineral. And I would call this situation somewhat unpleasant. And those geologists who will later try to analyze and interpret the results of my fieldwork, which I obtained using a laser spark analyzer, will probably rely on them quite heavily. Stronger, maybe even rather biting and salty words, to describe what actually came out in the end. So now we have two portable methods that you can take with you, but each of them already has its own limitations. Now let's consider a good method that lacks the drawbacks of both. This is optical emission spectrometry. It's a very old method, with a huge body of accumulated knowledge, and the analysis spot, it would seem, is quite large. And you can detect elements literally starting from hydrogen and helium, so... In fact, it's the spectrometer method that allowed us to know that the sun is made of helium and hydrogen, because the spectra were measured, processed, and there you have it. So there are no limitations like the ones I just mentioned regarding elements, no issues with the analysis spot, but immediately we run into the problem that the spark really needs argon or any inert environment. That means we can't just take it with us anywhere. Even the lightest and smallest optical emission spectrometer is neither light nor small. That's 20 to 30 kilograms for the device alone. And the gas cylinder it needs to operate is another thing entirely, another 20, 30 or even 40 kilograms. And out in the field, every kilogram weighs 1 kilogram at the start of the journey, but by the end of the journey, it feels like a whole ton. So, as always, there are pros and cons to everything. That's why we choose the task, and based on that, we solve it. The main thing is to choose the right method. That way you won't feel painfully regretful about money spent for nothing. And that's exactly what I wanted to talk about. So, XRF, what are its prospects, what are its advantages, and how can it help save a significant amount of time and money? But there are still situations where you can't do without other methods, even when you already have XRF.
Yes, Alexander, thank you. There are a lot of interesting points. You've touched on those points here. Going back to our matrix, yes, there are the field, the lab, and the production lines, right? On the one hand, and on the other, we have many different types of equipment based on various complex physical principles. And from a third perspective, we probably end up with a three-dimensional matrix. We also need to understand which elements we need to analyze. So it looks like we probably have a three-dimensional vector right here.
If we can add one more, let's add a fourth. Profitability, the methods.
Profitability, the economics. All right then. Here, I completely and utterly agree with you that Physics is structured and established in such a ruthless way that the absorption cross-section of light elements, when we examine the detailed data tables, Mendeleev's table, to the left of calcium, below the 20th element, it's 1,000 times less than that of metals. So all other things being equal, in order to detect light elements, we need, by default, to supply an intensity 1,000 times higher than for metals just to somehow compensate. This is the physics of it. The capture cross-section is inevitably smaller. So, of course, for X-ray radiation analysis, the golden standard is the use of heavy metals. Of course, in terms of our specific topic today, when flow analyzers are being utilized, especially if we're talking about copper or various polymetallic ores, such as zinc, lead, or tungsten, here the X-ray's golden standard definitely applies. It seems like this method was made exactly for that. It responds exceptionally well to metals. But naturally, if we begin to examine carbon or a light matrix, such as sulfur, phosphorus, silicon, aluminum, the reaction changes, which of course we can't avoid as they're present everywhere in small amounts. By then, we have already started to face some quite significant challenges with XRF. We have been working very hard on resolving this issue lately. So the hardware side is also evolving, including X-ray sources, which are becoming more powerful. In principle, this has become possible from a hardware perspective. It's been possible for a while now to detect aluminum, silicon, and sulfur. This has long been implemented in portable analyzers, just as it has in laboratory XRF devices. But still, the port is not implemented in the flowcharts. Although it would seem that everything is on the surface, it is in a portable analyzer, which means that our analysis is carried out point blank. Because of these specific factors, we remove the presence of air, which tends to absorb the weak characteristic radiation emitted from light elements. This enables us to accurately analyze these light elements. In laboratory analyzers, either vacuuming or a helium medium is used. This allows us to detect light elements. But in the ongoing development of our analyzer, we use a combination of both of these fundamental principles. We strive to be able to accurately analyze elements such as silicon, aluminum, and even sulfur directly in the flow. On the one hand, we try to minimize the distance so that there is as little air as possible between the components. On the other hand, in every instance where it is technically feasible, we flush the structural parts with helium to displace the atmospheric air. We have now successfully filed 2 separate patent applications specifically for the analysis of light elements in pulp. Of course, there is naturally a lot of skepticism from customers, primarily because this is a completely new and innovative concept. In fact, I truly think that absolutely no one else in the entire world has ever done this before. So in principle, that kind of reaction is entirely understandable and quite predictable. Here I've added a bit more detail to your introduction regarding the laboratory and the specific fields, supplementing it with what concerns our particular part of online analysis. Yes, we will certainly discuss this further as we go along. For now, let's touch on a closely related topic. A very interesting one is the analysis of slurries. It seems to be about the fields, but at the same time, it's also a process topic when you need to analyze on site, right in the field. It's a very challenging task, but probably an interesting and in-demand one in the long run as well. We'll come back to it. Later, we can take a look at it in the next podcast. I'd like to add a bit further about the depth of analysis. If we examine LIBS, NISO, or if we look at specific XRF, for example, XRF is compared to neutron analyzers. Skeptically speaking, when a neutron analyzer penetrates, its penetrating power is simply enormous. Yes, meaning it can scan, for example, the entire layer of ore, a large volume of pulp, when compared to the X-ray fluorescence analysis method, which has a significantly lower penetrating ability. But this depends on various conditions and on different elements. It can range from microns to millimeters depending on exactly which element we're analyzing and in what matrix. So it might seem insufficient in some cases. But at the same time, if we're talking about LIBS, both the depth and the area of analysis are relatively limited and localized. And this clearly presents significant challenges and inherent limitations when the environment is not homogeneous. If there is some segregation or some fragments present, then let's say with LIBS. It is important to note that the question of the representativeness of the analysis becomes a critical issue that must be addressed. I would also like to add for our viewers, for example, to further expand and elaborate on this topic of the inherent limitations of the LIBS method, because it really does seem very promising. The analyzer, what does it analyze? If you look, the prospectus says it analyzes, and the analysis range is good, the error margin is good, and the list of elements is extensive. But unfortunately, none of the brochures bothered to mention such critical technical nuances as area and depth. Before the analysis, there is such a concept as representativeness, and that is what you must consider.
About that, I would be happy to talk about that now. Well, let me start with what we can use. Even for XRF, we could take some kind of super powerful regional tube that would literally shine through not only our sample, but a lot more beyond it, whatever is behind it. The problem isn't in exciting the sample at a certain depth. The main challenge we face is that the signal we excite there has to travel back out to the surface so we can detect it. An analogy just came to mind. It doesn't really matter how deep you can dive if you can't swim back up. So, let's say we excite the sample so that it penetrates several centimeters deep. But the signal just won't make it out from there. That's why there's no point in chasing after too much tube power and no point in increasing it. All that muscle is literally unnecessary here. In other words, we can shout all we want, but it won't do any good. That's why it's important that we can at least cover a larger area and get more signal. Of course, we have to keep in mind that the sample may be heterogeneous not only along the lateral surface, but also in depth. But listen, you can't expect a method to do what it's not capable of. It's like expecting geophysics to provide an exact understanding of the mineral composition of rocks at depths of up to 20 to 30 kilometers. So, you scan everything, get some information, and say what layers are there, but what exactly are they made of? We can't answer that. The method simply isn't designed for that, just like XRF isn't meant for looking deep inside. So the real question we need to address here is exactly how to use this specific method. Let me give you a helpful analogy involving a powerful chainsaw. You take a chainsaw and in different hands the results vary wildly. This versatile tool can either be used by a master artist to create an amazing sculpture out of wood or ice, or it can be used to stage a scene from the Texas Chainsaw Massacre. A lot depends on the operator, and on how the operator handles the object, how well they understand what's happening, and how they approach the task at hand. The ideal geological sample, well, that is, if you really follow the proper methodology, is, of course, perfectly ground and thoroughly mixed. The entire process of sample preparation is, in itself, a separate and fascinating topic. And only then do we consider the result to be truly representative, absolutely and completely. But in practice, if you take the same sample and examine and study its entire surface area as thoroughly as possible, well, at least, what exactly does a professional geologist have to work with? They typically have a specialized analyzer at their disposal. And a geologist isn't really a geologist if they don't have a hammer. They break open the rock. Essentially, we've already gotten inside it. We analyze it across the entire surface area. And if you do, well, then we get the analysis results. Then we crush the same rock, press it, do all the necessary preparation, and the difference in accuracy and reproducibility of the results won't be that significant. I mean, of course, there will be some difference, and later, not in the field, but in the lab, people will definitely take care of that. But specifically in the field, when time, money, and the efforts of the staff are melting away before your eyes, this becomes critically important. So, it's precisely because of the ability to analyze a large surface area at once that XRF also gives us huge advantages.
Let's digress from the topic a bit. Actually, there are specialized analyzers that work specifically in the infrared range. Yes, but in fact that's the other extreme. If XRF has a limited yet nonetheless significant penetration depth, then in the visible optical range, and well, even the slightest little detail on the surface for us results in large errors.
The thing is, now we'll touch a bit on the topic of economics. By simply taking a heavy hammer and breaking the rock, and then breaking it again, and in this way, carefully studying its composition using a surface method is significantly faster and more efficient, cheaper, simpler, and clearer than using some completely new, complex method of analysis and literally trying to scan it all at once. This approach really doesn't lose out on much detail at all. So, well, the neutron method is, of course, excellent. The penetration depth is high. But say we penetrate a meter deep, and while the signal travels that meter down and then a meter back up, who can guarantee that it actually returned from exactly that depth and that we're really seeing what we want to see? That's also a question. In geophysics, there are similar analogies. We only see from the surface. In any case, we're not actually going deep. On the surface, what we see is essentially the solution to an inverse problem. There, you can create so many different situations that will give us this response. In fact, we can create an infinite number of such situations. You need boundary conditions, and that's the whole mess. So there's no need to reinvent the wheel where it's already been invented. XRF remains, despite its inherent technical limitations. The specific physical challenges you mentioned, like the very low luminosity of light elements, the need for specialized techniques with purging and so on, still make it one of the most highly efficient and reliable analytical methods, due to the unique combination of all these various factors. Even the limitations on light elements, if we touch a bit on mineralogical analysis, well, we can't see the very light elements, anything lighter than magnesium. For example, we definitely can't see lithium. We can assume, and I'm not a mineralogist at all, that lithium is present in certain minerals, while in other minerals there are already heavy elements present. So, in order to say, based on XRF analysis data, whether we have lithium there or not, well, it's not strictly necessary to see lithium itself. Maybe we'll see its closest companions, the ones it most likely hangs out with. Those we can detect using XRF. And so after conducting the analysis like this, there's still a huge question left. In the interpretation, if we interpret it correctly, we get the results we need. To look at it again, it is much like working with a chainsaw. The method certainly has its own inherent constraints and limitations. But if you operate the tool with the proper technique and adjust it correctly from a hardware perspective, and if the operator truly understands exactly what is occurring during the process, then sometimes you can even turn those same limitations into advantages.
That's the thought I wanted to ask you to elaborate on. In terms of laboratory analysis, there are optical emission and X-ray fluorescence analyzers. After all, X-ray fluorescence analyzers are also very popular for laboratory analysis. So what recommendations can you give from your practice, from your experience?
First of all, I'll say that if we are in a laboratory and there is no rush, then optical emission is usually several times cheaper. So,
why is that? What makes it so?
It's much simpler in its design. That is, the optical emission spectrometer itself is designed to be as simple as possible. It's a spark, and we've all seen it. We all watched it as kids, even though we were told not to do it with welding. Basically, we need to create the same kind of spark and split it. Well, you literally take a prism, a little triangle, and you need detectors. And that's already the simplest spectrometer. Of course, you can make it a bit more complicated. In fact, you have to make it more complex. That is, the source becomes programmable, and the lenses are made from rare, expensive materials. And instead of a prism, we have an ultra-precise grating, a diffraction grating, I mean. The matrix is some kind of super complex advanced one that needs to be cooled. But all these technologies are mass-produced. For example, the detectors used in optical emission can be found in professional cameras as well. And the market for even high-end professional cameras is orders of magnitude larger than the market for analytical equipment. Because each of us knows at least one lab technician, or spectrometrist, but 5, 7, even 10 photographers. So, the components needed for a spectrometer are produced on a much larger scale, which makes them significantly cheaper. And as a result, the device itself is also cheaper. And at the same time, because the method is very old, there is a huge body of accumulated knowledge. So basically, if some situation arises, instead of racking your brain and coming up with additional purging or upgrading the hardware, increasing the detector's counting speed, or something else, you can just Google the relevant article or video and get your answer. Of course, traditional emission optics are cost-effective. They are an older technology and very well tested, but they are also quite bulky. That is exactly why I mentioned that if you are working in a controlled laboratory setting and no one is in a particular hurry, then this remains the best way to go. But an important limitation is that there are also a huge number of optical emission spectrometers. And some of them can work with geological samples, while others can't work with them at all. So that's another point to consider. If your object of analysis is, first and foremost, metals, already finished alloys, then of course, optical emission is the way to go. You'll save on everything. It saves you time, money, and a lot of nerves, unlike with XRF. And in practically all of those other various cases, well, that's where the difficult questions really begin to arise, which unfortunately I simply can't answer, because when it comes to optical emission, I'm much more deeply focused on the field of metallurgy.
Alloys.
Yes.
Where homogeneity is important, right?
Well, where homogeneity is already present.
Yes.
Although, in fact, just today, at around 2 o'clock in the afternoon, a long and truly torturous week-long process finally came to an end, when the complex instrument was fully installed and properly set up. And after being absolutely sure that the instrument, well, it was definitely working. Well, it was certainly working without a doubt. But the specific data the user was getting back could only be described with one single word: terrible. And for a week we struggled with the question of why a good instrument was giving terrible data, what was wrong with it. And only when we assumed that the problem wasn't with the instrument, but with the supposedly homogeneous samples, did things finally start to move forward. So alloys have their own complexities and subtleties too, and a casting won't necessarily be perfectly uniform or homogeneous across the entirety of its surface. But here we come back to the point that even the best instrument in the wrong hands just ends up becoming furniture.
But
based on my years of professional experience, I would put it this way. XRF technology acts as a universal magic wand that can consistently determine the specific grade of a material with an extremely high level of accuracy. And then, with just a couple of button presses, you switch the device to work with rocks and immediately start analyzing them. But that's only if your task is specifically rapid analysis. Speed, by the way, is extremely important for on-stream analyzers, so here, XRF, well, basically for now, there are possible alternatives, but only in exceptional cases. So if you need speed and have a lot of samples, XRF is the best choice. But if it's not enough for you to just determine the grade of the material, and for metallurgists, especially foundry workers, this is extremely important because they are the ones actually producing this metal. And they need not only to know the grade, they also need a detailed chemical composition and a thorough breakdown of what exactly they have produced in the end. XRF won't help here, especially since in ferrous metallurgy, one of the most important elements is carbon, which XRF can't detect, or if it does, it's poor and slow. Plus, an XRF device that detects carbon is an order of magnitude more expensive than optical emission spectrometry. So in this case, optical emission is the way to go.
We can also distinguish between different processing stages, which might include, for example, agricultural fields or potentially mining operations at the later stage. We have the concentrators, the metallurgists, and if we're talking about alloys, then it's optical emission. Everything is homogeneous. If it's for a detailed laboratory analysis, or if it's a thorough expert assessment, then you can certainly use XRF as well. But you know what I was thinking about just now? After all, as we started out saying, it's really important to start from the specific task at hand, the specific task we are currently handling and the exact stage we're at. Whether we're working directly out in the field, at the concentration plant, or already at the metallurgical stage, are absolutely vital to our success. Secondly, depending on the specific type of production involved, we carefully evaluate and determine which elements are critical for us. For example, let's take a look at the cement industry. With carbon, yes, there, XRF analyzers are useless for continuous flow, so historically, neutron analyzers have been used instead. They are installed above conveyor belts like a kind of golden mean. Using this identical technical approach, experts are now attempting to install specialized neutron analyzers at industrial processing plants that handle various types of copper, zinc, and lead. And there are a lot of questions there as well that arise. So here, the neutron analyzer has a high penetrating ability. This is definitely an advantage, but every coin has two sides. On the other hand, we get a huge drawback, which is a significant, really major radiation hazard, which needs to be shielded. And this massive sarcophagus that is meticulously positioned directly over the neutron analyzer, that's several tons, weighing approximately 5, 6, or perhaps even 8 tons just for protection. That's exactly why I didn't mention the neutron analyzer at first. For fieldwork, you simply can't feasibly transport such heavy equipment anywhere with that kind of substantial shielding. This, probably like with homogeneous alloys in metallurgy, is simply not a practical or feasible solution for regular use. There are certain areas where neutron analyzers are used. It is certainly possible that there might even be a golden ratio for LIBS as well. Still, if we talk about XRF, the results are absolutely fantastic except for one major but. The issue of ionizing radiation remains a concern. In this regard, LIBS represents a bright and promising future for many people. How many of you have a fear of radiation? Yes, well, as the old saying goes, and as we all well know, even a stick shoots once a year, but what exactly do I encounter? Of course, most problems actually stem from simple misunderstanding, carelessness, or general negligence. So the very first thing, let's say, is that it's incredibly important to understand what is truly dangerous there and what is actually much less dangerous. There is, in terms of radiation levels, a specific scale, so to speak, for measuring these things. The potential to harm a person, the level of radiation can range from microsieverts, that's the dose, and that's the difference. Yes, we need to multiply by 1,000,000 if we compare it to what we're used to. If you look at a thermometer, 36.6 degrees Celsius is normal, 40 degrees Celsius means you should be lying down, and at 42 degrees Celsius you're basically dead. There's only a small difference. The percentage change at that level is, I don't know, less than 10%, just a few percent. If you go by that logic, if a person sees, say, a background value of 0.1 microsieverts, that's allowed there. For example, for categories of personnel who are exposed to significantly higher levels up to certain values, basically, if the number on the decimeter changes slightly, people might start to panic, but you don't panic when you're flying on a plane, even though the exposure there is 30 times higher. You have to understand that this scale, can go up to a sievert, which is 1,000,000 times higher. This isn't like a person's body temperature, which changes by 5 degrees, fluctuating around 35, which is quite insignificant. Here, it can vary within a very wide range and by a lot. Perhaps we've gotten a bit sidetracked, so let's get back to our topic and try to break it down. There are different areas. For example, we can distinguish light elements, those related to, say, the cement industry, lithium, as you mentioned, and so on. For these, for instance, there's a specific set of equipment. There we have some questions regarding XRF. For different tasks, it's important to keep in mind that XRF doesn't work particularly well with light elements, although in principle there is progress being made in this area.
So I'd like to continue that thought, but first I can't resist making a little jab at the radiophobes who think radiation is scary, but LIBS is great because there's no radiation involved. But on the other hand, if anything, the laser can burn your eyes out. So, well, here's another phobia to add to your collection. Right now, we're just registering laser analyzers in the state registry, and there's a specific laser safety class for them. Whoa, that's a fun topic.
Yeah, so...
Well, now let's get back to the fact that light elements are an issue for XRF. There are situations where this suddenly becomes a relevant, seemingly problematic issue. But I want to defend XRF a little now, the method in general, and process analyzers in particular. And to return to the point that these light elements don't occur on their own. That is, lithium is contained in some, I don't know which, mineral, which is made up not only of lithium, but also of other elements that, among other things, XRF will detect. And of course, we can't guarantee that we'll see lithium there, but if, like, we're always together with Tamara, and if Tamara is there, then I'm probably somewhere nearby too. Yes, in a couple of cases, she might be alone. Somewhere, well, she's on her own, I'm on my own, but that's not the point. But if our XRF data are consistently stable and highly reproducible, and we've ensured that when the ore composition changes, our signal changes accordingly, and we've properly calibrated the instrument, and in this respect, XRF is a remarkably flexible method. And once it's set up correctly on site, it will remain robust enough to forgive many different mistakes. We will solve our task of searching for light elements simply by using the satellite elements. Well, let's take a not-so-light element, lithium, and a heavy element, gold. The gold content in ore is, well, about 1 gram per ton, maybe 2 grams per ton. That's so little, XRF won't be able to detect it. And even more so, you still need to take a sample that actually contains that 1 gram. Well, that's an unsolvable problem. And yet, we do detect gold, including for gold mining companies, who are actually some of our favorite clients, because they don't count their money and they buy a lot of equipment. But we won't do that. We're not going to process everything just for that 1 gram per ton. But we will find trace elements, minerals, indicators, and understand that yes, there is probably gold. The problem is solved, that's it. It's the same with lithium. If you use XRF, your device, it's good at what XRF is generally good at, which is detecting elements. In your case, from calcium and heavier, this method will work well for solving such problems. These are the kinds of practical tasks we're talking about. And if XRF is bad, then no matter how much you try to tweak it, it will still perform poorly overall. So the real questions are about the setup, about how well the people who make and implement the device understand the method's limitations and what to do about those limitations.
The topic of gold is probably very interesting and relevant right now, because it's once again breaking historical price records. There's a very interesting situation with gold. In what way is it interesting for us, for process analyzers? That is, almost all enterprises in Russia that mine copper, nickel, lead, zinc, they are all equipped with process analyzers. And almost all gold mining enterprises, of which there are a huge number in Russia, are not equipped with process analyzers at all. In other words, nothing has even started there yet. From this point of view, yes, we do have limitations. Another thing, by the way, dear viewers, is that the range in which we work is very important for each method. For example, in XRF, this is the data. For example, hundredths of a percent and higher. So you see, you simply cannot do a direct analysis. For gold, where it's a gram per ton, that's 4 decimal places. At the very least, we're still off by 2 orders of magnitude. But all gold extraction plants, all of them need direct gold analysis. But at the same time, there are enterprises where mineralogically there is an excellent correlation. For copper and arsenic, I talked to colleagues from the plant. They say, well, we don't even determine gold. We determine arsenic and copper, and we have a formula by which we recalculate. In principle, it works wonderfully for a number of deposits where this is possible, where there is a single mineral and the correlation is excellent. But here it's very interesting to expand on this topic from the point of view that at various conferences and exhibitions, I periodically meet with technologists from gold extraction plants and say, well, we make on-stream analyzers. All the enterprises that mine metals have been using them for probably 2 or 3 decades already. Why don't you use them? Well, everyone just shrugs and says they don't know, even though it would seem this is about efficiency. Efficiency. In the end, it's about money. Through the lens of your experience working with portable analyzers, as I understand it, this is mostly about geology, when geological exploration is being conducted at gold deposits.
Yes.
Yes. So these are not industrial processing facilities. What we are seeing is still geology.
It just so happened historically in our company that we have 2 very strong geologists. Well, 2 very strong ones and 1 more, well, part-time, myself. The guys, well, they themselves started out as field geologists, geological prospectors. And of course, their circle of contacts, their network, is mostly metallurgists. Not mineral processors, but prospectors. If the guys had chosen different specialties back in the day, maybe now we'd be specializing in mining and processing plants, but fate just worked out this way. But still, yes, because it's these highly portable and advanced handheld devices that are used in specialized geological exploration and field research work. They have become so widespread and are almost completely irreplaceable, because this allows the team to obtain extremely valuable and detailed scientific information in the form of chemical composition, and to some extent the mineralogical composition of the rocks they are currently traversing, or the sections they have found directly right there on the spot in real time. Thus, confirming or refuting a previously made hypothesis about the geological structure of the area where they are currently working, and immediately, in real time, in a literal sense and in real time if it becomes necessary, they can recalibrate their intended route and modify their work plan. So, without this vital source of information, the only tools a geologist has available are their eyes and a hammer. And, well, if he was an excellent student, he correctly identifies the rock, its mineral composition, and accordingly the chemistry, and knows what's what and what to do. But the quality of education is declining. And even when it isn't, for every really good specialist, there are a couple of not so good ones. And such a consistently impartial analysis in X-ray. At that point, it hardly depends on the operator anymore, as long as he's been properly and extensively trained in the necessary procedures. His task is, he reaches the cross-section, gets the analysis and sends it via satellite phone. He immediately calls the base, where smart people are sitting and making decisions. And right away, he either goes ahead and continues according to the plan, or he adjusts the plan. That's it. And all of this happens in absolute real time, so any potential downtime is kept to a minimum. But before XRF, or for those who still haven't acquired XRF for some reason, well, people would just manually collect physical samples. You decided that one way or another, you absolutely had to send something for laboratory analysis to confirm your hypotheses. And then, while the sample is being delivered to the lab, that takes, well, a week. Okay, maybe it's just a few days, or maybe it's a week. And during those days or weeks, the batch might either be moving in the right direction, which is great, and we're happy about it, but it could just as easily be moving in completely the wrong direction. Or if we play it safe, it might just sit there and wait. And in the best case scenario, that means the batch is simply sitting idle, but in the worst case, it could have triggered technical issues that really shouldn't have happened. And that is literally just throwing away money for absolutely nothing. This drastically reduces the economic efficiency of the operation, because batches mean people. People need to be fed, they need to be supplied with electricity or fuel. In short, their livelihoods need to be maintained. They need to be paid salaries. And really, it's much better to spend all these valuable resources on productive work, rather than on inactivity or, even worse, on inefficient work. And this specific ability to make decisions right in the course of work and adjust the action plan is actually far more valuable than the analyzer itself.
You know, Alexander, what you're saying about efficiency reminds me of an analogy. It's a similar situation at mining and processing plants when an on-stream analyzer is installed. In fact, every plant has, historically speaking, a laboratory has been established. By the time we take a sample, even though it's located nearby, it takes about 3 hours, given the volume of ore being processed. The volume is huge, so in those 2 or 3 hours, by the time we get the post-mortem analysis, first of all, it only has an indirect relation to what's happening right now. Secondly, in those 2 or 3 hours, we lose a certain amount of time and fail to take the right actions that could have corrected the outcome. Generally speaking, that's how it is. But honestly, I haven't come across a plant being designed or built nowadays where an inline analyzer isn't included from the start. Naturally, there is always a laboratory available, but inline analyzers are also integrated directly into the system. So, it is a very, very similar analogy to what we see in the fields. We really can, so to speak, have several hours of reduced quality levels, where we might release or lose material, metal, or tailings. And in just those few hours, the losses can truly be enormous and significant.
You're absolutely right. Whether it's a geological team, a mining and processing plant, or anything else. Right now, we're all about high labor productivity and all these wonderful topics. This is the time that we spend to make sure everything is running smoothly. This directly affects the speed of decision making. And the faster we have information, in essence, the speed at which we receive information is directly correlated with work efficiency. If it's a matter of seconds, then efficiency is at its maximum. If it's hours, well, in an hour, you are absolutely right about that. You can end up making such a mess of things that all you can do is feel sad about it. That's why all these methods are being implemented. But if a questionnaire is put together by an engineer, purely by an engineer, then I put myself in the client's shoes. I need a hygrometer, meaning I need to measure humidity in a certain gas. And I want to see a questionnaire that asks, what do you need? Humidity. What are the limits? What kind of gas? Just the basics, no details. But the questionnaire was such that instead of the 5 questions you'd expect to see, there were 30 or 40. Even with my pretty solid education, I had to Google half of them. So, no, it's a mess. Speaking from a general perspective, as someone from a sales organization, I would like the equipment selection matrix to be designed such that the very first step in any case is a direct consultation between the person who will be working with the equipment, or rather the person responsible for solving the specific task for which the equipment is being purchased, and someone who truly understands this equipment. That is, well, it is not just our company that receives a significant amount of negative feedback in this regard. Just tell me the price. I do not want to leave my contact information. A lot of arguments have happened over this, actually. We have a collection of truly masterpiece emails like these that we receive from satisfied users. The thing is, first of all, any analytical equipment, well, it's not like a broom. Even within the same model, the spectrometers that I personally assemble in the department that I head, my spectrometer can cost from X. Still, I can't tell you the price, you see? from X to 4X, even though they look identical on the outside depending on what tasks need to be solved and with what precision the setup itself, the configuration, the software and what's hidden under the hood can be completely different. So, well, it's really hard to name a price. That's just me saying a little in my own defense. Basically, the person who is solving the problem and the person who understands the equipment, that's the very first step in any case. Because how does it look right now? People on the shop floor complain to upper management. Upper management somehow understands something, puts together a request, sends it to the purchasers. The purchasers also interpret it in their own way. And then they put together the technical specifications, and based on those specs, then we have a competitive bidding process, and they buy the cheapest thing that meets all the necessary technical requirements. And as a result, instead of the people on the shop floor who originally raised the issue, smiling and solving the problem after some time, well, they're struggling and suffering. Unfortunately, I've seen such people myself when I came to install the units and conduct training. You want people to be happy with their brand new piece of equipment. But I saw tears in the eyes of the girl at the entrance, because there was no communication between this girl, who took the initiative herself and who, in the end, is the one held responsible for making sure the problem gets solved. But the problem won't be solved, because instead of giving her what she wanted, they bought something she didn't really need, by the way, 4 times more expensive than what would have actually helped them. And in the end, well, it all goes to waste. Unfortunately,
my colleague and I discussed this on the previous podcast. This is probably one of the main and most painful issues. It was the topic that prompted me to start recording these videos, because I also remember specific instances when various people actually buy famous branded equipment worth several $1,000,000. And then they just end up writing it off without ever using it. I really feel that your point resonates deeply with me, that this is highly sophisticated, high-tech and science-intensive equipment. Sometimes I get the distinct impression that certain technical specialists treat it like a basic axe. You buy it and then you just simply start chopping away at wood with it. And also, if we consider the cost of this equipment, people often compare it to cars, and it seems like basically you just get in and, roughly speaking, put it on autopilot. You don't have to do anything at all. I'm exaggerating a bit, but that's the gist of it. You just need to understand that, for example, if we take XRF, even a single detector is a real marvel. It's high-tech, a kind of pinnacle of technological development. When we have and inside there's a vacuum and cooling down to minus 50 degrees with a small Peltier refrigerator. And when we have a beryllium window that's vacuum tight or graphene, in other words, it's one advanced technology layered on top of another. And some tiny part the size of a thimble basically costs as much as a car. It does seem a bit absurd, right? How can a thimble-sized object cost as much as a big car? But unfortunately, most of us have probably encountered this too, that there's this widely held and common layperson's attitude that if something is really that expensive, it should do everything completely automatically by itself. But here, as a rule, the paradox is that it's exactly the opposite. That it requires, first of all, if not to say careful handling, in our case, our device itself, despite all its delicacy, fragility, and so on. The construction is such that, thankfully, in theory and principle, it allows us to work even at high temperatures, in high humidity, in dirty environments when we install it in the field and so on. But then again, there's a bit of a dissonance. If it works physically, then the data you get is a completely different story. Quite often, our process of optimization has reached such an extreme level that they try to assign complex methodological tasks to the on-site technical specialist. You'll be the one responsible for calibrating it. From this perspective, it is an exceptionally rare group of individuals who can be both highly skilled and deeply knowledgeable in terms of the ACSTP team. If something doesn't turn on or there's a failure somewhere, they can find, identify, and fix that failure. In terms of calibrating the analyzer, they also need to be exceptionally well trained and highly skilled, understanding when, so to speak, we have relevant data, carefully taking various subtle nuances into account, consistently monitoring the system, conducting control sampling, and generally understanding how accurately the analyzer is currently displaying and reporting the final results. Unfortunately, there are a lot of these nuances as well. There are so many, but with the current optimization and shortage of human resources, of course, at factories and especially out in the fields, There just isn't a dedicated person to handle these methodological issues. I found myself really liking and was truly struck by a particular comment. The head of the ACS service at Uchali Mining and Processing Plant, now already retired, Dmitry Demidov, while we had a methodologist, we had an XRF analyzer installed above the conveyor belt. It was a metrological instrument. As soon as the methodologist retired, that analyzer turned into just an indicator. This really reflects the approach. It all needs to be done consciously. We tell our clients, we're not trying to impose our services on you, for example, specifically regarding remote metrological support. But in that specific case, please make sure that someone on your end is actively handling and taking care of this issue. Because if you just install the device and calibrate it at a few points, most likely after a certain period of time without proper monitoring and ongoing technical support, it will be, at the very least, extremely difficult to get the maximum possible benefit from it. Because the place where it's installed, usually in production, things tend to change. It's not a constant. The product might change, or the site itself could be modified. So we constantly encounter this, the fact that nothing in production is static either. Everything is subject to some kind of change, and let's say when a person is not a specialist, but from their point of view, they might think, for example, that the height was changed, raised, or they just think it's just a device. It was hanging straight down, but now we are applying it at an angle. For them, it doesn't matter. It makes no difference. But methodologically, that's it. It is a completely different situation. The original calibration set for this position implies that if you hang it roughly horizontally, you won't get the same results back.
I support everything you've said, and I'd like to add from myself that with all these nuances, for example, the graphene detector, the Liberally detector, people start to get bogged down, stressing over what's better, what comes first, and in the end, they miss the forest for the trees. So, coming back to the matrix, well, okay, let's say we didn't succeed. It's precisely about connecting the responsible person with someone who can help and advise. In that case, you need to rely on what you want to do and where you want to do it. And also in what time frame you want to do it. Because we can obtain a diagram, so to speak, quite affordably and very quickly. But the point is, only the specific combination of the task, the time, and the place will give us what we need. A good proper result. That's why there's a saying about not using a microscope to hammer in nails. At the very least, you need a clear, as precise as possible understanding, not of which device you want, but of what problem you want to solve. That should be the cornerstone of the matrix. Because choosing your equipment without first having an honest conversation with yourself about what you really want from it is a major mistake.
That joke you mentioned, it's about cheap, fast, high quality. Pick two options.
Yes, exactly. Right, exactly here.
Yes. But, I'm coming back to my example. For example, at various gold extraction processing plants, they invested in expensive on-stream analyzers, but unfortunately, they found that they were not actually able to achieve the maximum benefit from them as they had originally hoped. They bought some top-of-the-line equipment, and here again, from the perspective of the matrix, the choice is a significant investment. Buying the most high-end equipment doesn't always mean it's the most effective or appropriate choice for you. It's not a given that it will actually serve you well. In fact, it's probably more reasonable to take an approach of starting with simple solutions and moving to complex ones.
Absolutely right. Here's a simple analogy with a car. We need something with 4 wheels that can transport a certain load from point A to point B. This is a very generalized task without any details, and I have 2 options: a Bugatti for a lot of money and a Niva. But I really love and respect my company, I'm very successful, I have a lot of money, so I'll buy the top option, I'll buy the Bugatti. And then it turns out that the cargo is just bags of potatoes, they don't even fit in it, and I ended up overpaying for something I don't even need. But
driving on a potholed dirt road where the Bugatti can't go.
It just can't. There you go. So we've elegantly come back to where we started, that there are no good or bad methods, no good or bad equipment. There are only things that are suitable or not suitable for the task. How elegantly...
Another question, Alexander. Everything seems to be right on the surface. You're absolutely right. Whoever is going to use it should talk, consult, But do you know what the paradox is? The paradox? Because even very large companies with a huge number of employees, the question is, getting to the truth, how does it actually happen, and at what specific stage does the failure occur? When a company invests a significant amount of money, buys some very expensive equipment or software and then gets absolutely zero benefit from it. The point of our discussion is to explore this topic in depth and provide clear guidance to help you, on the one hand, avoid making such an incredibly expensive mistake for nothing. Not only is it a matter of wasting the company's valuable time, resources, and money, that's just one side of the issue. On the other hand, it's also incredibly important to convey and highlight that sophisticated, high-tech, and science-intensive equipment requires highly skilled specialists who can actually work with it effectively. To put it simply, you can shoot a sparrow with a small slingshot, or you can choose to fire a massive howitzer and still completely miss your target. This level of personal experience and professional expertise also play an absolutely critical and fundamental role in achieving success. Or, as current practice shows, probably about 70 to 80% of our clients still sign contracts for methodological support and remote technical assistance. Fortunately, modern times and telecommunications tools make this possible. Yes, they allow you to make high-quality video calls and quickly access a workstation remotely. Yes, so all of this has now become possible, and it's really great when you can help clients and provide technical support remotely so they don't have to look for someone on their own permanent staff. Now, especially now, of course, it's very difficult to attract such highly skilled specialists to cities where, let's say, the climate isn't exactly the most favorable or comfortable for living, even probably for a lot of money.
I'm flying to Nakotka soon. It's like a knife to the heart. Regarding the problem you just mentioned, I personally believe that, of course, the client is very interested in solving it. But expecting these people to understand every single detail and make the choice themselves is a bit unfair. I firmly believe that a great deal of responsibility lies with us as manufacturers to ensure that these people have all the information they truly need. We're not just sitting here for show, we're trying to discuss and explain the importance of making the right choice. On the contrary, I believe that if you're doing something and doing it well, you should promote it. And people need information about what things are and how they work. Objectively conveying information to people is a matter of conscience, and it's about whether you want to work for the long term or just quickly sell everything you managed to bring from China and then disappear into the mist. There are plenty of people who do that too. This is especially problematic now because the market is changing rapidly, and there are a huge number of new companies bringing in a vast array of new products and equipment. The competition is fierce, and if you put yourself in the shoes of a customer who just wants to analyze, say, a rock sample or a metal, they go online, and all you can do is feel sorry for them. Because the amount of informational noise, often not even honest, that gets dumped on them is just... it's a nightmare. Well, looking at it at this point, let's give ourselves a bit of well-deserved credit here, in the sense that we deliver entirely unbiased and objective information. In some cases, this can actually lead to losing a client. For example, Company A reaches out to Company B and said, "We'll definitely solve your problem, just give us the money and we'll all be happy." But Company B, well, listen, here we are with you. You see, X-rays as such can't detect light elements, but theirs supposedly can. Honestly, that's physically impossible. For them, it's possible. And the fact that physics, well, you know, that in one company physics works one way, and in another it works differently, it's very hard to get that across. But you really have to try. In the end, those who engage in dishonest or unethical business practices will only ever get clients once. And those who sincerely put in the hard work and effort, I want to believe this at least, will have people returning to seek their services again and again. But for that to happen, we really need to, as manufacturers, make the effort ourselves and not shift all the responsibility onto the client. Yeah, it's a bitter truth. But in this case, when it comes to choosing equipment, expensive equipment, the bitter truth is actually much more reasonable than a sweet lie. And right now, there are still far more sweet lies.
Yes, absolutely. And that's one of the reasons we are recording this video, to do our part and help customers make the right choice for their needs, to help guide our customers a bit more on different tasks, suggest where they can turn for support and so on. But I think I'll move from my general message to something more specific, what we've actually encountered, starting with the first example. Let's imagine a large modern factory that was built relatively recently, and they needed to install a specific analyzer directly at the control point. They ended up choosing a Chinese manufacturer. Now, the colleagues there are quite unhappy with the results. Basically, Unfortunately, that's when we got to know them. Afterwards, they basically said to us, unfortunately, where exactly were you before this? So first of all, regarding our PR efforts, even though we have been active on the market since the year 2012, which is already 12 long years now, to my great surprise, there are still many people I meet at various industry conferences. When new factories are being built, there are colleagues who, basically, even now, they are simply not aware of our specialized equipment. That is the first major point. The second point I want to mention is about what happens when mistakes are eventually made. Think about it this way. You know, it is probably not just a matter of shifting responsibility or being unwilling to help the client. Rather, it is more about the lack of any clear, formal guidelines or specific directions to follow in this situation. I'm talking about gold extraction plants now, specifically regarding the process analyzers. You see, here is what happened. So, let's say a company bought an expensive analyzer, but it didn't work out. What happens then in that year? In January, we got another market benchmark report from the marketing team. And to be completely honest, that is what is so disappointing about this situation. The exact same mistakes were made over and over, but absolutely no real conclusions were ever drawn, and everything just kept going on exactly as it had before. It is in this very same vein and along this familiar, well-trodden path that I want to reach out to you in this video today. There could even be a separate podcast series about this topic specifically for gold extraction plants, so that people who are just getting into this field or are already involved have some solid reference points when it comes to making their choices. Because when this task is generalized and handed down to marketers to conduct a market benchmark and analysis, well, judging by the structure of the document we received, I really hope I'm wrong. But it seemed to me that with a high degree of probability, the company will end up making the same mistakes again. So how do we get through and convey this information about what actually exists? You don't need to chase after everything and try to cover the impossible. You need to start small and move forward step by step. That's the challenge. The point is simply that the goal of recording these video podcasts is to convey this information to these people and to tell them about us, that we exist, that we've been doing this for more than 10 years, that there are people you can turn to and consult with, and that probably with a certain degree of confidence, we won't just try to start a conversation just to sell you something, somehow, some way. Are you looking for some small additional bonus opportunities in Cyprus along with a premium component? As it often happens in this industry, unfortunately, there are actually quite a lot of such interesting and challenging tasks out there waiting to be completed. And, well, for example, this is probably our distinguishing feature. If we talk about real-time online analysis, there is a large class of tasks, including gold analysis in the stream. Regarding ZFs, we've approached this task several times. There have been successful industrial trials and so on. But I won't go into the complex economic background as to why, after all, specialized tools for increasing operational efficiency are still not widely used at gold extraction plants today. There are also various other tasks. For example, in the field of metallurgy, such as the detailed analysis of iron, silicon, and calcium. When analyzing iron ore raw materials during the process of loading them into a blast furnace, a sophisticated neutron analyzer is also commonly used there. But right now we're working on an interesting project. And I actually believe in this idea that we will probably arrive at such a standard solution, not immediately, but probably within 5 to 10 years. In fact, there are already projects that have been implemented. When we take material from the conveyor belt, crush it, and feed it onto a parallel bypass conveyor, where in principle you can perfectly well install an XRF, which will determine silicon, calcium, and iron for you, and all other things being equal, this will be a good alternative to a neutron analyzer. But again, you need to look strictly at the specific task. Sometimes a neutron analyzer might be the better choice, sometimes this one. And this solution can be used as an alternative. And probably there are such tasks that in principle have not yet emerged methodologically or technically in the market. So they, in a manner of speaking, They are buried under heavy layers of complex bureaucracy or deep-seated pessimism, and so on, but there are also a great many of them in our society. That is, I have probably mentioned two of the most pressing tasks: for the analysis of gold deposits or for the detailed analysis of various iron ore raw materials. This has also become significantly more relevant recently, but as a matter of fact, there are a great many such diverse tasks in material analysis with various streams and directions that can be further developed. Now, Alexander, moving forward, I would like to bring our insightful conversation to a comprehensive conclusion, probably within the specific context of our three-dimensional matrix. Let's say, depending on the physics where we are, whether it's at the mining site, in the fields, in beneficiation, or in metallurgy, then along the matrix with elements ranging from light to heavy, and in that context, beginning right from where we first started, XRF, LIBS, and sophisticated optical emission spectrometers. But it would probably be best for us to start by first looking at the full range of elements. Yes, we've come to the conclusion that if we're dealing with elements from calcium to uranium, we primarily look at XRF. For open fields, for raw steel, for professional metallurgists, and for detailed analysis, whenever speed and mobility are needed.
Yes, first and foremost, we take into account that different methods have different capabilities when it comes to detecting elements. And here, the question we ask ourselves when choosing is exactly how significant these elements are to us. To put it quite literally, do we need to see their signal, quantify it, and provide a comprehensive chemical breakdown? Or are indirect methods sufficient for us? Because, well, my XRF doesn't detect carbon in high alloy stainless steel. There's basically no carbon there. Well, if the method doesn't detect the element, then how critically important is it for us that the method does detect this element? Does the task require it? Or maybe the opposite. And in geology, actually, especially for geological exploration, first of all, not all elements are equally important. In general, to see the whole picture, we actually don't see anything at all. But in reality, we see quite a lot with XRF, from magnesium to uranium. The information from XRF, especially if you're out in the field and you're a geologist, is enough for you to make the right decision and understand what to do next. Actually, the elements themselves, as such, that's what I would focus on. Only when the task specifically requires that the elements are really needed, important, and absolutely essential. Nowadays, many people, even those working with XRF, because of this very competitive mess, have started writing in the state register that they can detect elements starting from sodium. But that's still somewhat forgivable, although in reality, it's not forgivable at all. Up to curium. And curium is, well, it's an artificially synthesized element that you can't find in nature. And a person with an XRF prototype wouldn't even get close to curium. Oh, actually, not even curium, californium. That is, it's something that costs billions of dollars per gram. Generally speaking, a broad variety of elements is often far from enough. Well, at least for a more limited and not so wide range of tasks. And often, you can determine something by indirect methods. That's the first point. The second point, if the elements are still important and necessary, consider where you will be working and how urgently you need the data. Because here we run into the issue of portability, which gives us speed in decision-making versus accuracy, since anything portable will always be less accurate than something stationary and well-calibrated. Well, specially calibrated. This also comes down to the specific task. So now that we have identified the core elements, we have figured out the need for speed. But where will you be working? Buying a portable XRF for the lab when a stationary one is several times cheaper than a portable one. So there are a lot of factors to consider. And such a unified matrix, really, the kind you'd want to create, like literally make a questionnaire, yes or no, like Akinator, that anyone could go through to make the right choice. Unfortunately, as our conversation went on, I realized that for now it's very difficult to formalize. And nothing can replace talking to someone who has already been through all of this and really figured it out. You don't necessarily need to be extremely well read to make the right choice if you can find someone who already has that knowledge. And as for the matrix, well, we're not going to create a matrix. Yes, and no one else will either.
Perhaps it's possible to set some direction and highlight some key points, like how to distinguish things, sort wheat from chaff.
Well, to put it as simply as possible, if you're working in the field, you need a portable XRF. Don't even consider LIBS, the data will be terrible. And even more so, don't even think about OS. you'll curse the day you bought OS for geology. If you're working in a laboratory, don't consider portable devices. You'll end up paying more for worse data, so why would you do that? If you're working with metals and alloys, don't look at anything except OS, because it's cheaper, more efficient, and more accurate. But if you work with metals and alloys, and at the same time it just so happens that you work in some kind of industrial diagnostics, and your analysis objects are towers, bridges, and so on. Things like that which you can't bring into a laboratory, then and only then should you consider LIBS. If we really sum up everything we've talked about, then in very broad strokes, it can be outlined like this.
I'd probably like to add something about correlation, especially when it comes to processing plants. From my own experience and that of my colleagues and partners, we constantly encounter this. There are some correlation dependencies for silicon and so on. But to be honest, so far our colleagues at the plants don't really believe in this. Yes, so specifically for processing plants, this topic doesn't really work. Everyone wants to see direct analysis of light elements. For some, this can be critical for certain series, maybe for silicon. So we've taken this task very seriously and have been working on it for several years, focusing on real-time XRF analysis of light elements. Yes, it is possible with a neutron analyzer, but there are a whole bunch of issues there, both in terms of radiation safety, methodological problems, and so on. It seems that everything works out on the surface, since laboratory portable devices have been reliably determining these for a long time. Attempts have been made to apply this approach in flow analysis on slurry streams, where in principle the sample is homogenized, already sufficiently ground, and this analysis can be performed. The same applies to the analysis of bulk materials on a conveyor belt. Even there, it works provided that the material maintains a consistent particle size distribution. If it's an agglomerate, suppose for a moment it's mixed with limestone and coal arranged in distinct layers. Even then, this approach of taking and extracting the entire mass still holds true and applies. For example, using a cross-stream sampler from the conveyor belt, grinding it, this method probably also has its place under certain circumstances when performing XRF analysis. Alexander, thank you so much for such an interesting and insightful conversation. I truly hope that this material will, at the very least, be very helpful for our viewers. Let's say conceptually, yes, it helps to set some markers or lay out the general directions. This is particularly relevant regarding the choice of equipment for various tasks. We really broadened the discussion with you going left and right from our main topic of process analysis, taking a look around, exploring beyond just laboratory analysis. Therefore, I truly believe that this material will be incredibly beneficial to our viewers and will provide them with great value in the long run. But
if even one geologist watches this and, instead of buying a laser spark spectrometer, chooses an XRF for their fields, I'll already be so happy and know that all of this was not in vain.
Specifically for all of our loyal viewers and subscribers, Alexander and I have recently come up with a special secret word. Podcast. Please be sure to mention this word to the team to receive better terms or additional exclusive discounts when you are contacting the company. Thank you all so much for watching. We would be happy and grateful for your comments under the video, your questions, and your feedback. Please write to us if you have anything to add, supplement, or elaborate on. Or on the contrary, if there's a topic we haven't covered and you're interested in it, we would also appreciate those comments. Thank you for your attention.
Thank you for your attention.